Welcome, I'm David Fuentes Jimenez from the University of Alcalá, and today I will present the tutorial Ultrasound Distance Measurement using RubyBoard as part of the work of Ruby Team Project Partner from University of Alcalá and part of Erasmus Plus GEMS project. In this lecture, I will guide you through ultrasound fundamentals and how we can measure distance in an Arduino platform using real cases. This lecture is structured as follows. First, we will review the objectives and key concepts of ultrasound. Next, we will discuss the nature of sound waves, their properties in air, and what ultrasound actually is. We will then analyze the ultrasound module, covering its transmitter, receiver, and the methodology to compute distance. Finally, we will review an example applications, code breakdown, and conclude with key findings and references. Let's begin with the course objectives. Our primary objective is to understand the principles behind ultrasound distance measurement. Next, we will learn how to generate and capture ultrasonic pulse, calculate the echo time, and ultimately convert that into a distance measurement. Finally, we will demonstrate how to implement this technique using RubyBoard and Arduino platform. In this section of basic concepts, we will start with ultrasound waves. Ultrasound waves are mechanical waves that have frequencies above the audible range for humans, in which particle displacement is parallel to the direction of propagation. In air, these waves are transmitted through the collisions of air molecules and at room temperature, around 20 degrees. The speed of sound is approximately 343 meters per second. Understand these fundamentals is crucial for accurate distance estimation using ultrasound. In our context, the ultrasound module used, specifically the HC-SR04, emits an ultrasonic pulse that collides with the objects in the emission direction, and then receives its echo pulse that is an attenuated and delayed version of the emitted pulse. The time delay between the emitted pulse and the received echo, combined with the known speed of sound, allows us to calculate the distance from the collided object. Finally, we will find the desired distance measurement by using the transmitted and received pulse train. Now let's review the basic setup of the ultrasound module. The HC-SR04 comprises a transmitter which emits the ultrasound pulse and a receiver which detects the received echo. This sensor is composed of 4 different pins: the power pins, the ground pins, and the 2 remaining ones that are the key parameters of the sensor, whose are the trigger signal, which is a short pulse that initiates the measurement, and the echo signal, whose high duration is proportional to the distance. This module is capable of measuring distance from 2 cm to 400 cm with high accuracy, often up to 3 mm. In this page, we can visualize the workflow of HC-SR04, including the timing between the trigger, emission, and receiving echo. It is important to mention that the minimum trigger height time is 10 microseconds and that the distance measurement is coded as the width of the square signal obtained in the echo pin. Moving on to the practical sample, our objective is to measure distance using the HC-SR04. The module is interfaced with an SCP32. A power WM output pin is used to send a trigger pulse, while another pin listens for the echo. The code continuously reads the echo pulse width, computes the distance using the speed of the sounds, and visualizes the distance both via serial output and through Charlie-Plexin-based LED display. Let's break down the code. In the initialization phase, we define key constants and variables such as the ultrasound pins, the height time for the trigger pulse, and the maximum distance measurable. All the defined constants are key values to a correct measurement and visualization in the next steps. We also set up the LED pins for Charlie-Plexin visualization. During the setup, serial communication is initialized and all necessary pins are configured as outputs or inputs accordingly. In the loop function, the microcontroller sends a trigger pulse by setting the trigger pin height for a specific duration and then load. Immediately afterwards, it measures the duration from which the echo pin remains high. This duration is then converted into a distance. The compute distance is displayed via the serial monitor and represented on the LED display using a function that maps the distance to discrete levels using Charlie-Plexin. Next, we focus on the visualization component. The level display function quantises the measured distance into levels, each corresponding to a different LED configuration. By using chartreplexing, the limited number of microcontroller pins can control multiple levels, each pattern representing a specific range of distance. This method not only efficiently uses hardware resources but also provides an intuitive visual feedback of the measurement process. In this slide, we propose you to create a distance measurement system that measures objects at 200 and 400 centimeters. After that, you have to find the error between estimated and real distances. Finally, you will have to represent visually the distance using chartreplexed LEDs and binary codification. To summarize, today we have explored the essential principles behind the ultrasonic distance measurement and its practical implementations using the HC-SR04 module in RubyBoard. We have learned the physics of ultrasound waves, the operational mechanisms of the ultrasound module, and the innovative use of chartreplexing for visual feedback. This course provides a solid foundation for designing robust, low-cost sensing applications in robotics and mechatronics. Thank you for your attention. If you have any questions or need further clarifications, please refer to a reference provided in the presentation. We encourage you to experiment with the concepts and tools discussed today, and we look forward to seeing how you apply these techniques in your projects.